Hello student friends, today we are going to start with properties of convolutional sum. By this time we have finished the examples and basic concepts related to convolutional sum. That is, we have completed examples on discrete type convolution. Now let's understand the properties of convolutional sum in the sense that if a complex system is there which consists of multiple subsystems and they are interconnected in different manners, then how we can convert it into a simple form or in a singular unit. Similarly, there are certain system classifications. If you recall in unit number 2, that is systems, we have seen certain classification of the systems. So as we are aware that convolution is applicable to LTI system, the remaining system classification like static, dynamic, causal, non-causal, stable, unstable, all these we try to find out with the help of impulse response. So in unit 2 we have seen this classification based on input-output characteristics. Now we are going to study the same classification but now using impulse responses. So let's start with the first point. So let's start with properties of convolutional sum. We are having in all three properties: commutative property, distributive property and associative property. So let's start with the first property, commutative property. Commutative property tells us a very simple thing, that if we convolve two signal x and h, the result will be always same. So their position does not matter. That means y of n, that is output of the system, is equal to x of n convolved with h of n, where x of n is input and h of n is impulse response, as you can see in the first diagram. Same output y of n we can get from another system which has got input h of n and now impulse response is x of n. So in simple manner, commutative property tells us that the input and impulse response, if they swap, still the result remains same. So this is what the meaning of commutative property. Here is the proof of commutative property. Let's start with the representation or notation and definition of convolution. That is, y of n is equal to x of n convolved with h of n, and it is defined as summation k goes from minus infinity to infinity x of k into h of n minus k. So this is notation and definition of convolutional sum. So what we are going to do is, as you can see, x is the input, so its main variable n is replaced by dummy variable k. But for impulse response, its main variable n is replaced by a variable n minus k. Now I am supposed to swap input and impulse response. That means h should have main variable replaced by dummy variable, whereas x should have main variable replaced by n minus k kind of thing, or main variable minus dummy variable. So let's start with the simple substitution for this proof. Let n minus k is replaced by some variable m. So k will be replaced by n minus m. Now due to this change, the limits will also get changed. So when k approaches to infinity, it tells that m approaches to minus infinity, and when k approaches to plus infinity, m approaches to minus infinity. Now let's substitute all these limits to the upper equation or the above equation. So what we will get, y of n is equal to summation, now new variable will be m. Summation m goes from infinity to minus infinity, x of n minus m into h of n. Now let's make some adjustment. So if you are going to sum four numbers, so their a sequence will not matter. That means you are summing from first to last or last to first, the result is going to remain same. So that's why the limit of summation, which is from plus infinity to minus infinity, I can change it from minus infinity to plus infinity. So we can change this index. Second thing, multiplication is also commutative. So x of x into h, that I can swap. So it can be written as y of n is equal to summation m goes from minus infinity to infinity h of m into x of n minus m. Now if you look at, it's again a definition of convolution. So where h is convolved with x. So using the definition of convolution, you can write down y of n is equal to h of n convolved with x of n. So we started with x of n convolved with y h of n, and now we end with h of n convolved with x of n. So here is the proof of convolutional sum, first property, commutative property. Here is the second property, that is distributive property. This property is also known as parallel connection of systems. So here, if two systems are connected in parallel, then their impulse responses gets added. This is actually the meaning of this system. As you can see in the block diagram, if we have input x that is applied simultaneously to two systems h1 and h2, and their outputs are added together to get a resultant output, then we say that the two systems are connected in parallel. So this whole system can be replaced by a single system which is having the impulse response h1 plus h2. So in this case, we can say the statement as y of n is equal to x of n convolved with h1n plus x of n convolved with h2n. This is the output of first system. Same output I can get from second system, which will give the output as x of n convolved with a bracket h1n plus h2n. So the meaning is important in this case. So what the meaning is, if two systems are connected in parallel, then their impulse responses gets added together. This is what the distributive property is. Now let's go for its proof. Now to prove the distributive property, or to prove any property of convolution or any transform, whatever we will be studying in this subject, remember that the basic definition we should apply first. So here you can see that the output of the first system is y of n, which is equal to x of n convolved with h of n plus x of n convolved with h2n. So here we will substitute the definition of convolution in this case. So what I will have is, for first term, I will have summation k goes from minus infinity to infinity x of k into h1 of n minus k. Similarly, second convolution will be replaced by its definition, summation k goes from minus infinity to infinity x of k into h2 of n minus k. Now from these two summations, you can see that the summation sign as well as x can be taken common. So to the next step, that is in the third equation, you can see that y of n is equal to summation k goes from minus infinity to infinity x of k into bracket we have h1 of n minus k plus h2 n minus k. Now this itself is a definition of convolution. The first sequence is as it is, second sequence is folded and shifted. So it's a definition of convolution. So using the definition of convolution, I can say that first sequence x is convolved with this bracket term. So what is there in the bracket term? h1 and h2 addition. Therefore y of n can be written as x of n convolved with h1n plus h2n. So this is the simple proof of distributive property of convolutional sum. Now the third property is known as associative property. This is also known as series connection of the systems or cascading of the systems. The cascading means output of previous stage is given as an input to the next stage, and the final output is taken from the last stage. So this is what is known as cascade or series. So you can see in the first block diagram that we are having two systems, h1 and h2, or their impulse responses are h1 and h2, and output of first system is given as input to the next system, and finally from second system we get the output y of it. So this whole system or this subsystem interconnection can be replaced by a single system. And what will be the overall impulse response of this subsystem or final system will be? So it's convolution of individual impulse responses. So you can see that in the second block diagram that the overall impulse response of this system is h1n convolved with h2n. So what the meaning we understand from it, if two systems, or if the systems are connected in series or cascade, it can be replaced by a single system which is having an impulse response as convolution of their individual impulse responses. So we are considering only two systems. So the statement can be written as y of n is equal to x of n convolved with h1n. So this is the output of first system. that will act as an input to the second system. Therefore, x1n convolved with h1n, this whole term will get convolved with second system impulse response, that is h2n. So what of statement I have? Y of n is equal to x of n convolved with h1n. This whole is convolved with h2n. Now this can be replaced by a single system, and what the output of that system will be? So what will be the output of second system? It is x of n convolved with, and what should be in the bracket? h1n convolved with h2n. So the statement is y of n is equal to x of n convolved with h1n. This whole bracket convolved with h2n is same as x of n convolved with bracket h1n convolved with h2n. So this is the statement of associative property. Again I am repeating, statements are not that important. What is important is what the conclusion we have taken from it, or what the meaning we understand from it. Now previous two proofs, that is commutative and distributive, these proofs are quite easier to understand, but this associative property proof is that way slightly difficult. In the beginning only we are going to assign certain names to some convolutional functions. For example, what is the output of first system? Output of first subsystem is x of n convolved with h1n. So that I will replace by some different name. So I am going to call it as f1n. So let f1n is equal to x of n convolved with h1n. Similarly, for second block diagram in the previous slide, the impulse response is h1n convolved with h2n. So that impulse response h1n convolved with h2n, we will be giving another name that is called as f2n. So we have defined two functions, f1 and f2. So now as per the statement is y of n is equal to x of n convolved with h1n. This whole bracket is convolved with h2n. So x of n convolved with h1n can be replaced by f1n as we have assumed. That's why y of n is equal to f1n convolved with h2n. Now let's use the definition of convolutional sum. So y of n is equal to summation k goes from minus infinity to infinity f1k into h2 of n minus k. Now let's use the definition of f1k. What is f1k? f1k is convolution of x and h1. So let's replace it. So I can say that f1k is equal to x1k convolved with h1 of k. So how can I represent it now? So we will have f1k is equal to summation k goes from minus infinity to infinity x of m into h1 of m minus k. So what I am doing? I am using the definition of convolution. Why? Because f1 function f1 itself is a convolution of x and h1. So we are replacing that now. So let's replace this function f1k in the above equation, and now what we have in the y of n is two summations. So y of n is equal to outer summation k goes from minus infinity to infinity, inner summation m goes from minus infinity to infinity x1m into h1 of m minus k. The summation is completed, multiplied by h2 of n minus k. So here we substituted the definition of convolution for f1k. Now the remaining proof we will see in the next slide. Now in the previous slide we have seen that the output equation y of n is now represented with the help of two summations, right? So one summation has variable k and another summation has variable m. So the summation with variable m has got term x of m into h1 of m minus k. So let's make some adjustments in it. So this m minus k terms, let's replace it by some another variable p. So k will be written as p plus m or m plus p. So as m approaches to infinity, p will approach to infinity, m approaches to minus infinity, p will approach to minus infinity. It means that there is no change in the limits. So if we substitute this in the above equation, the equation can be rewritten as y of n is equal to outer summation k with respect to, or goes from minus infinity to infinity, p goes from minus infinity to infinity x of m into h1 of p multiplied by h2 of n minus m minus p. Now what we have done, we replace all the terms which has got k with the help of p or p plus m likewise. So now what we are going to do is we are going to interchange these summations again. So let's take x of m outside the summation p, because it does not have variable p, so that can be treated as constant and that will come outside the second summation but inside the first summation. So what remains in the second summation is summation p goes from minus infinity to infinity h1p into h2 of n minus m minus p. Now this itself is a definition of convolution. So h1 and h2 we are convolving with each other, and convolution of h1 and h2 we have given a name as f2. So if you recall in the last slide, in the beginning of this proof we have defined two functions. X and h1 convolution we called as f1, and h2 and h1 convolution we called as f2. So this is the definition of a convolution f2. And what is the main variable of convolution? P is a dummy variable, so what remains is n minus m. So this is h1 convolved with h2 with a variable n minus m. So h1 convolved with h2 we have given a name as f2. So it's a definition of f2 with a variable n minus m. So what we have finally in the equation, so y of n is equal to summation k goes from minus infinity to infinity x of n into f2 of n minus m. So using the definition of convolution. Now if you look at this equation, this summation a k goes from minus infinity to infinity x of m into f2 of n minus n, this itself is again a definition of convolution. So in this case it's a convolution between x and f2. So I can write down it as x of m convolved with f2 of n. What is f2 of n? As we defined in the beginning, it's h1n convolved with h2n. So finally we have y of n is equal to x of n convolved with bracket h1n convolved with h2n. So here we completed the proof of associative property. I'm requesting you all to write down this proof again on your own, so that it will be easier for you to derive it. Okay? And if you have any difficulty, you can ask the doubts either on WhatsApp or in the Google Classroom or in VOL. Now in last few slides we have seen properties of convolutional sum. Now in this slide we will be studying the impulse convolution properties. So whenever we convolve the impulse with any signal, what happens? Let's understand that. So we will first use the definition of impulse response. So what it says, that if you apply an input to a LTI system as impulse, the output will be an impulse response. So it is shown in the first diagram that if the input is del n, the output will be h of n. So what it says, if input is del n, output will be h of n, because it's a definition of impulse response. Input is input, then whatever output we get, that we called as impulse response, and it is denoted by h of n. So when I apply del n as an input, I get output as h of n. Now what I will do is same system. That means how I get the output? The output is convolution of input and impulse response. So it is del n convolved with h of n. So what I get? Y of n is equal to del of n convolved with h of n, which again results into h of n. Now look at the same diagram. I replace with a small change, that h of n is replaced by x of n. So what I will get at the output? So at the output I will get x of n, because h of n is replaced by x of n. And how the output is? Output is input and impulse response are convolved with each other. So del n convolved with x of n, what results into? Again as x of n. So simple concept we got, x of n convolved with del n is equal to x of n. So that means when we convolve impulse with any signal, the signal remains same. So this is the very important property of convolution of impulse. that whenever impulse get convolved with any signal, the resultant signal remains same. Now same concept we extend. See, this is shifted impulse. Now our system is the LTI system, meaning is linear time invariant system. So let's use the concept of time invariance. So what time invariance is, if there is a shift in the input, same shift reflects in the output. Now look at the first diagram. Del n applied as an input to the system h of n, output is h of n. So when I apply del n, output is h of n. Now I am applying del n minus k as an input. So output will be h only, but there is a time shift. So what I will get? H of n minus k. So del of n minus k when applied to the system h of n, output is h of n minus k. Same adjustment now. H of n replaced by x of n. So what I will get? Del of n minus k when applied to a system which has got impulse response x of n, output will be equal to x of n minus k. And how I got this output? So it's a convolution of these two, that is del n minus k convolved with xn. So what I got? Xn convolved with del n minus k is equal to x of n minus k. So what the property tells us now, if a signal is convolved with a shifted impulse, the signal nature remains same, only there is a shift in the signal. So input or signal convolved with shifted impulse result into shifted signal. So I hope you understand these two properties very well, because these two are important properties of convolution. Based on the properties that we have seen in the last few slides, we will start with the example. The example is, for the system shown in the figure, find overall impulse response. So that means you are supposed to calculate final h of n of it and evaluate the response if the impulse responses are. So you have given h1n, h2n, h3n, different impulse responses values, and based on that you are supposed to tell or find out the final value of impulse response. So here we have given that h2n and h3n are connected in parallel, and the input to this is output of first system, that is this h1n is in cascade with h2n and h3n. So parallel connection of h2n and h3n is in cascade with h1n. So what will be the resultant h of n? Let's find out in the next slide. So step by step let's use the properties and reduce this overall system representation into a single system. So as we said, h2n and h3n are connected in parallel. So the distributive property tells us that when the two systems are connected in parallel, their impulse responses should get added together. Therefore what we get, h1n plus h2n will be the resultant impulse response of the new subsystem. So that was shown in the second figure or second block diagram. So what the result we have, or finally what we will get, x of n applied as an input to h1n, that is output of that system is applied as a input to the next system. Now these two systems are connected in series, that is h1n and h2n plus h3n. These two systems are connected in series. So when two systems are connected in series, as per the series or cascade connection of the system, it should get convolved with each other. Therefore h1n will get convolved with h2n plus h3n. So here it is, finally the complete system will be having an impulse response h1n convolved with h2n plus h3n. So here we find out the impulse response of overall system. Now in the next slide we will use the values given to us and let's evaluate the impulse response. Now we have what we got finally is h of n is equal to h1n convolved with h2n plus h3n. Let's substitute the values given to us. So h1 is replaced by del n minus 2, h2n is replaced by u of n plus 2, and h3n is replaced by minus of u of n minus 3. Now let's give this convolution separately to these two. So what we have, del n minus 2 convolved with u of n plus 2 minus del n minus 2 convolved with u of n minus 3. So using the concept of impulse convolution, what we say is x of n convolved with del of n minus k is equal to x of n minus k. So that's why for first convolution u of n plus 2 is there, so its n will be replaced by n minus 2. So what we have finally is u of n minus 2 plus 2. So minus 2 plus 2 will get cancelled out and we will get the output as u of n. So the first convolution results into u of n. For the second one, del n minus 2 convolved with u of n minus 3. So that u of n, that n will be replaced by n minus 2. So it will be n minus 2 minus 3 will become n minus 5. So what we have finally is u of n minus 5. So we have h of n is equal to u of n minus u of n minus 5. So this is the resultant impulse response that we have got. Now this example is homework for you. Here again you can see some parallel connection and series connections. So what you can do is you can name them as h1n, h2n, h3n and h4n, and then you can perform or you can represent the system by overall impulse response h of n and then evaluate by using the equations given to you. So try out this. If required, I will provide the answer of this later to you. After completing the properties of convolutional sum, now we are here to classify the system based on the impulse responses. In unit 2, we have seen systems where we classified the system based on the input-output characteristics, right? Now here we will classify the system based on impulse response. So there is a difference between input-output representation and impulse response representation. So please try to check this difference. So in this case, what we are going to do is, as our system is a LTI system, so it's by default linear, it's by default time invariant. So what classification remains are static dynamic, causal non-causal and stable unstable. So let's represent the system by using, or let's classify the system under these categories. Here for this classification, we will be using the commutative property of impulse response, that y of n is equal to x of n convolved with h of n is same as h of n convolved with x of n, and when I say it is h of n convolved with x of n, that can be written as summation k goes from minus infinity to infinity h of k into x of n minus k. So this definition we will be using, not x of k into h of n minus k. So that's a small point to be noted, that I am using commutative property of convolution, and all the proofs will be derived by using this property. So let's start with the static system justification, or how we understand whether the system is static or dynamic based on impulse response. So what we are going to do is, this summation is there that we split into three parts. The first part will have all the k index as negative, second part has k index as 0, and third part has k index as positive. So when summation k goes from minus infinity to infinity, h of k into x of n minus k is there. So this x of n minus k for negative values of k actually represents the future input. So it is x of n minus k, where k is negative, represents advance operation, right? X of n minus k, where k is negative, represents advance operation, and as it is an advance operation, the advance term represents future inputs, right? Second split represents k is equal to 0. So it is summation k is equal to 0 h of k into x of n, right? So x of n represents what? X of represents your present signal or present input. Similarly, summation k goes from minus infinity to infinity where k is positive values. H of k into x of n minus k. So for positive values of k, x of n minus k represents a delayed terms, which are your past terms. So that means the first summation and the last summation represents outputs due to future input or past inputs. But when we say a system as static system, the output of the system must depend only on present input. So when it should depend on present input and not on past and future values of input, the first and last summation answer should be 0. So what we can say is y of n must be equal to, or y of n results into h of 0 into x of n. No summation is required because it's a single term. So it's a h of 0 into x of n. That is the resultant y of n, because output should depend only on present value. Now if you look at the impulse response term h, its value is present only for 0, and a signal which presents only for 0 we called it as impulse. So the condition that we get is, for a static system the impulse response must have the nature which is same as impulse itself. Therefore h of n is equal to c times del n. If this is the form of impulse response, c times del n only, not a shifted impulse, normal del n, then we say that the system is a static system. So what is the takeaway from this complete slide? The takeaway is, when the impulse response is of the form impulse itself, then we say that the system is a static system. So this is the condition for static system on impulse response. Now let's start with the second classification of the system based on impulse response, and that is causal systems. So how we define causal system? A system for which output depends on present or past values of input but not on future values of input is called as causal system. So here we have got the representation of output in terms of commutative property again. So y of n is equal to x of n convolved with h of n is equal to summation k goes from minus infinity to infinity h of k into x of n minus k. Again split this summation into three parts for different values or index values, that is k negative, k 0, k positive. So when k is 0, that summation represents output due to future input. When k is equal to 0, that is output due to present input, and when k is equal to positive, that is output due to past input. So what we say? We say that output should be 0 for future input. That means first summation should be 0, remaining two summations will generate the output. So for static system, y of n is equal to summation k goes from minus infinity to infinity h of k into x of n minus k, plus summation k goes from 1 to infinity h of k into x of n minus k. Now this represents output for causal system. So on which terms of impulse response output does not depend? So it does not depend on negative values of h. So what the condition we got? So for causal system the impulse response must be 0 for negative values of n, that is h of n is 0 for n less than 0. This is the condition that we get for causal system impulse response. So this is the condition on impulse response for causal system. Now let's start with third classification of the system, that is stability or stable unstable systems based on impulse response. So this is something called as stability criteria of DT-LTI system. This is the famous criteria mostly used while designing the systems. So we have seen that we called a system as stable if it satisfies a bounded input bounded output criteria, that is BIBO criteria. So when we say system as stable, when for a bounded input, if your system produces bounded or finite output, then it is called as BIBO system or stable system. So what is the criteria for it? So your input x of n, so magnitude of it must be less than some value m suffix x, where m suffix x is always a finite value, and whenever I'm going to apply that input will be always finite. That's why it is written for all n. So x of n, mod of x of n is less than mx for all n, that is the input criteria first, is applied as an input to LT ID system, that is linear time invariant discrete system with impulse response h of n. Then the output magnitude can be given as, so we are using the definition of convolution again, using a commutative property and applying mod for all. So mod of y of n is equal to mod of x of n convolved with h of n, which is mod of summation k goes from minus infinity to infinity h of k into x of n minus k. So now we have got the term that is in the form of magnitude of the sum. So first you add all the values and then take its magnitude. That is what this equation says. Now if I interchange the sum and magnitude, what I get? So if I first take a magnitude and then sum of the numbers, then the result is always greater than or equal to the magnitude of sum. That means first I sum and then take its mod. So the statement goes like this: the sum of magnitudes is always greater than magnitude of sum. So if I interchange the summation and mod operator, what I got is this sum value of mod is always greater, and that's why what we have is mod of y of n is less than or equal to summation k goes from minus infinity to infinity of mod of h of k into x of n minus k. And now if I give mod separately for the process of multiplication, or first I multiply and then I apply a mod, the result will not change. Hence I can separately give mod to h and x. Now in this case we say that x of n should be always less than m suffix x. Now if I consider that every time I am applying the maximum value of input, that is m suffix x, what the result will be. Let's understand that in the next slide. Please remember how I change this mod and sum. That statement is important, that magnitude of sum is always less than sum of magnitudes. So let's continue the proof in the next slide. So in this case, or in the previous equation, what we are going to do is the input which is there, that is x of n minus k or magnitude of x of n minus k, it's the shifted input. But whether it is a original input or shifted input, irrespective of that, whenever I'm going to apply the input to the system, I'm going to take care that the input will be always finite. So I'm going to replace it by m suffix x. So when I will be replacing it by m suffix x, what the result will be? So here that magnitude of y of n will be less than or equal to m suffix x into summation k goes from minus infinity to infinity mod of h of k. Now what we want, that system should be stable. When a system will be stable, when the output will be less than infinity. Now when the output will be less than infinity, so I have got two terms, mx and summation term. Mx is already a finite term, so what remains is the summation. So the point up to which this summation of magnitude of impulse response is less than infinity, the output y will be always less than infinity. That means output will be always bounded. So the statement is, it is clear from the above expression that for the output y of n to be bounded, the summation k goes from minus infinity to infinity, mod of h of k needs to be bounded. The condition or stability condition therefore can be stated as if the impulse response h of n of dt LTI system or LTID system satisfies the following condition, that summation n goes from minus infinity to infinity, mod of h of n is less than infinity, then we say that the system is Bibo stable system. So this is stability criteria of DT LTI system. Now let us cross check few of the examples based on the points or topic that we have seen, that is classification of system using impulse response. So the example will be of this type: determine the stability, causality and a static dynamic condition of the LTI system with the following impulse responses. So you should classify whether the system falls under these categories based on its impulse response. So we have got three examples. First one is h of n is equal to cos n into u of n. Second is 2 raised to n into u of minus n. And third is u of n plus 2 minus u of n minus 3. So let's start with the first example. So the first example is h of n is equal to cos n into u of n. So first understand the job of u of n. What u of n does, whenever any signal is multiplied by u of n, the signal nature on the positive axis is retained as it is, and negative axis part is cut down, that means it made as 0. So what we have is a cos function on positive or for positive values of n. So my signal will start from 0, goes up to infinity, and what will be its nature? It will be a cosine wave. So start with the first one. Once we understand the nature of impulse response, now we can start with the classification. So the first is static system. For static system, the condition for static system is that your impulse response h of n must have a nature c del n. So h of n is equal to c del n. That is the condition that we have seen for static system. But whether this system is of the form impulse, so it's a cos wave, obviously it's not an impulse. So that's why h of n is not equal to c del n. That's why it is not a static system, so it becomes a dynamic system. So this is the reason behind it. So how we provide the reason? In the form of mathematical condition, h of n is not equal to c del n. So this becomes my condition. Second, causality. So for causal systems, we have seen the condition that h of n must be 0 for negative time axis or negative values of n. So as the function is multiplied by u of n, it is having all values 0 for n less than 0. So it satisfies the condition that h of n is 0 for n less than 0. So as condition is satisfied, it must be a causal system. And now for third, that is stable system. So for stability, we have seen the criteria that if we add all the samples of impulse response or magnitude of impulse response, then if the result comes to be less than infinity, it is said to be a stable system. Now in our case, it's a cos wave. So if we substitute the function, it is summation n goes from minus infinity to infinity, mod of cos n into u of n. What u of n will do? It will restrict the signal from 0. That's why the limit of summation will start from 0. So we have got 0 summation n starting from 0 to infinity of cos n. So cos values or magnitude of cos, if when we take, even though cos has got positive values as well as negative values, magnitude will convert all of them into positive. So the summation of all infinite samples will result into infinity. So as the summation value is infinity, the system will become unstable, because the condition for stability is summation of this magnitude of impulse response should be finite. This is infinite right now, that's why it will become an unstable system. Now let us start with second example. H of n is equal to 2 raised to n into u of minus n. U of minus n is folded step. So our normal step function starts from 0 to infinity. Folded step will start from minus infinity to 0. So this is about u of minus n. What about 2 raised to n? 2 raised to n is of the form a raised to n, where a is greater than 1. So it is exponentially a rising function. So it's exponentially rising function but multiplied by u of minus n. That means only its negative axis part will be taken. So negative values of n or index n will be chosen. So it is exponentially rising from minus infinity to 0. Now for this system, first understand the static condition. So it's exponential function, it's not in the form of impulse. So what I can say is h of n is not equal to c del n. That's why it is dynamic function or dynamic system. Second, causal. For causality, condition is that impulse response should be 0 for n less than 0. So on negative axis there should not be any value of impulse response, but this whole function is available only on negative time axis. That's why it is non-causal. To be more precise, when it is present only for negative time axis, it is called as anti-causal, opposite of causal. So this system is one step ahead of non-causal. It's anti-causal system actually. Okay, but for simplicity we have given it as non-causal. And the third is addition of all samples. Now for stability, it's summation of all magnitude of all samples of the impulse response. Now if you add all of them, these impulse response samples will start from 0 and goes up to 1, because it's on negative time axis and it's exponentially rising function. So exponentially rising function is having value 0 at minus infinity and 1 at 0. So if you use a GP series equation, it is actually 1 plus half plus 1 by 4 and so on. So it is half raised to n. So half raised to n summation going from 0 to infinity can be written as 1 upon 1 minus half will become 2. So the summation value will be 2, which is less than infinity. Hence the system will become a stable system. Okay? I hope you can simplify a GP series for this. Now here is the last example. H of n is equal to u of n plus 2 minus u of n minus 3. I hope in the first unit we have seen how to sketch these signals. So the first step function starts from minus 2 and second step function starts at 3. So if I subtract these two step functions, I will get a rectangular function which will start from minus 2 to plus 2. So it will have 5 samples in it, right? So its nature is not of the kind impulse, it's a kind of rect. So that's why h of n is not equal to c del n, hence it's a dynamic system. Next, causal. For causality, condition is impulse response should be 0 on negative axis. But here I have got some samples on negative axis, so h of n is not 0 for n less than 0. That's why it is non-causal system. And the last, if I add all the magnitudes of them, so I have got 5 samples and all of them are positive, so their magnitudes will be again positive. So 5 ones are there, and if I add them, result will be 5, which is less than infinity. Hence the system will be a stable system. This is how you are expected to give the reasons or solve it. Specifically for stable system, you are supposed to solve this summation and prove that whether the value is finite or infinite, so that you will get a marks. So this kind of simple question can be asked for 4 marks to classify the system based on impulse response. Here are few of the examples for homework. So I have chosen 4 examples, 5 examples for you people. Try them whether it is satisfies the condition of stability, causality and static dynamic, and accordingly you can write down. Now as you are aware that we don't know up to how many days we will be in a lockdown situation, and we are supposed to complete our tutorials. For tutorials we require some sort of interaction, but now we don't have that much time. So I request you people to complete this homework and submit it as a part, because your C will be evaluated based on this homeworks. So all of you are requested to complete the homework, and when you will be coming for the college, when college will reopen, at that time you are supposed to submit your notebooks to me so that I can check and give you a continuous assessment marks based on it. Okay? So thank you very much. Here we finish with unit number 3, first half, that is DTLTI system, and the next lecture onward we will start with continuous time convolution, that is convolutional integral. Okay, have a nice day. Thank you very much for listening.